Hi friends, and welcome back to the Control Engineering Geek. Today we are going to talk about root locus using an example with complex zeros and poles. Let's start it. We have this transfer function here. This is the open loop transfer function of a given control system. This transfer function has 2 zeros and 3 poles. The zeros and the poles are complex, and we are going to learn how to draw root locus for such systems. First, we need to know some general information about the system. We have the number of poles. We have 3 poles. The poles are at -2 real root and 2 pure imaginary roots. Therefore, we have 3 branches. We're going to need to draw 3 branches for this system. For the zeros, we have 2 zeros. They are pure complex zeros at -3 plus minus 1.7 j. So, if we compute the number of zeros at infinity, we're going to have 1 0 at infinity. Let's do the characteristic equation. The characteristic equation is given by 1 plus kgh equal to 0. It is important to mention that here in this system we are drawing the root locus for changes in the control action or the control gain k that varies from 0 to infinity. Using this formula of characteristic equation of the closed loop system and using this given transfer function or open loop gain, we can substitute this in the equation here and find the characteristic equation. This characteristic equation will be useful when we try to know if the branches are crossing the imaginary axis. One last piece of information: we need to know the numerator and denominator derivatives with respect to the Laplace transform S as well. We're gonna need this to find the break-in and breakaway points later. Let's go to the second point, which we need to compute the asymptotes. We need to know the focus of the asymptotes or the position of the asymptotes, which is given by this formula. The algebraic sum of the poles minus the algebraic sum of the zeros multiplied by the difference between number of poles and zeros. If we use the roots we saw earlier, we can find that the focus or the starting point of the asymptotes is at +4. Since we have 1 0 at infinity, we're going to need to know at what angle does the branch go to the infinity. So it will be usually 180. If you do the computation here, k will be 0. This is just an integer. It doesn't have any work with the gain. K that we are drawing the root locus for it is just an integer. This integer depends on the value of the q. Q we have here is 1, so it will start from 0. Let's say the q has value of 3, then the k will start from the values of 0, 1 and 2. Okay, so the k depends on the q, which is the number of the zeros at infinity. Okay, let's compute the breakaway and break-in points on the real axis. This is very easy. You use this formula here. Those components are computed previously in the first step. So just substitute these values here and then try to find the roots of the resulted polynomial. Okay, this is the polynomial. This polynomial is of order 4, so we will have 4 roots. 4 roots, 1 at 0, not surprising because we have s common. We can factor out the s out here, and we will have 3 other roots. Two of them are complex, so those will not be useful. We may use the 0 or may use minus 0.8, or we may not use any one of them. It depends on the branches and the location of the poles and zeros. MATLAB code, the MATLAB code for computing this equation is very easy. I'm just using Asymptotes tools of MATLAB, and this is the piece of the code that I used to find out these roots here. Okay, let's jump out to the number 4, angle of departure from complex poles. The formula for finding such angles is given here. This is the angle that we need to know from the corresponding pole. Okay, for example, we have pole of P of J. So this equal to 180 degrees plus the summation of angles that zeros make with that corresponding pole minus the summation of angles that the other poles do with the corresponding pole without considering the pole itself. Okay, we don't take that pole in consideration. Applying this, we're gonna try to do it geometrically. So we have the map of the zeros and poles. These are the poles and zeros of this transfer function. Let's say we need to know, we have to know the angle of the departure from this pole here. Okay, denote that as a θ1. So what we are doing here is try to find the angles from the other roots to this corresponding pole here. So let's do from this pole, this will be θ2. We know we have another pole here. Let's say that this is θ3, and we have these two zeros here. So we have angle θ4 and angle θ5. Okay, the computation of these angles are easy. You just use the geometric tan inverse with the geometrics you have here. The distances are, all the distance can be known from the values of the poles and zeros we computed previously. Applying the formula we saw first here, the formula will be 180 degrees plus the angles that made by the zero from the zeros with the corresponding pole here minus the angles that are made by the other poles. We have pole zero θ2 and θ3. Okay, these are the values that we can use to compute θ2 through θ5 and then use it to find the θ1. The computations are done here. We have θ4. This is the formula of θ4 using the data here. Okay, all the way to θ3. If you apply the formula here, you're gonna find that the angle of departure from the pole θ1 is 104 and something degrees. Okay, although this is not necessary, but let us illustrate how to find the angle θ1 as well. So we have θ1 is unknown. Draw the angles from the other poles and zeros to this corresponding pole we have here. So we have θ2. Always compute the angle counterclockwise from the horizontal axis here. So we have θ2, we have θ3. Observe how the angles are computed or considered here, and of course for θ4 and θ5. The formula will be theta 4 and 5. These the angles are coming from the poles, from the zeros to the corresponding pole, and theta 2 and theta 3 are the angles that coming from the poles with the corresponding pole theta 1. So these are the geometric that we can use to compute the values. One important point here is theta 2, you don't need to compute it, it's already 270, but the other parts have to be computed. As you can see, you can check this out using the geometry here. Okay, if you computed these values and substitute in this formula here, you're going to find out that theta 1 from this corresponding pure imaginary pole is 255.8 degree. You can reach this value easily using the angle from theta from pole 1 when we have the pole plus 2.23j we computed previously by just subtracting 360 from that corresponding value theta 1, and you easily get this one. Okay, so what I've done here is just to show or to prove that this formula gives the same value here, or this value here is true when you compute it from this formula here. So once you computed one pole, the angle from one complex pole, whether it's complex or pure imaginary, you just subtract 360 from that value and you're going to get the other one because they are conjugated. Okay, let's now work with the angle of arrival at complex zeros. The formula is the same, okay, although you may see it's minus then a plus, but it's the same phenomena. It's 180 plus the angles that made by other poles with the corresponding zero minus the summation of the angle that made by the other zeros with the corresponding zero. Of course, we don't consider the corresponding zero itself. So one more time, we're going to go to the zero pole map. This is theta 1. We need to know the angle here, theta 1, which is unknown. Draw the angles from the other roots to that corresponding zero. Of course, like before, you can write the formula. This is the summation from other pole now. Previously it was other zeros. Then we have here other poles. We have pole the 3, 4, and 5 minus theta 2, which is coming from the zero. Okay, I can use this formula here, or this geometry here, to compute the corresponding values of theta 3 through theta 5, which are given by those formula here. Okay, you may use a different way to find theta 3, theta 4, and theta 5, but I use this one here and showing here for you. You can check well and compare it with whatever we got from here. So do our computation. Say now that theta 1 that coming for corresponding zero here, this zero, 526.5 degree or 166.5 degree. Once again, you can do computation for theta 1 from the other pole, from the other zero as well, with this formula given, okay, and those geometries here, which is an extra step to do because we have a simple formula. This one here, you can use the previous value of theta 1, subtract from 360, you're going to get the same value here. This is the easiest way to find the angle of departure and arrival from complex roots. The last point is to find the locus crossing the imaginary axis. So we use the characteristic equation we formulated previously and make use of the Rouse-Hurwitz criterion do the column or the table of the Routh-Hurwitz criterion. Let me remind you that if the Routh-Hurwitz criterion or the table, if the first column has an item of 0, this means that we may have a pure imaginary root, or we have a point on the imaginary axis. So using this point, we need to know if we have any value of k that makes an item of the first column here equal to 0. Of course, we have 3 of them. Let's start with the second one here. This, if we compute it like this way here, or like this formula here, we may have 2 values of k equal to 0 or k equal to -5/6. Okay, 0 will give you the same poles and zeros we got previously, and k -5/6 is out of the range that we are considering in this example, because we are concerned about the values of k that change from 0 to infinity. So it is non-negative values of k. This is negative, so it's already out of range. We don't need to compute further computations here. For the last part here, 10 plus 12k equal to 0. This also, so the last part here, 10 plus 12k equal to 0, also gives a negative value of k, so this is also out of the range. One may ask why we didn't take this 2 plus k. This is obvious, also gives a negative value of k, which will be k minus 2. All of these items here will give negative values of k, which all are out of the range of consideration of k here. So we will not have any cross with the imaginary axis with the corresponding values of k from the Routh-Hurwitz criterion. So far we have these informations about this transfer function. We have the poles, zeros, and we have 3 zeros. 2 are finite and 1 at infinity. We have the asymptotes point at 4 with an angle of 180. We have breakaway points, 4 roots of them. Just we may take the 0 or minus 0.83. We have the angle of departures and angles of arrivals, and we know we don't have any cross with the imaginary axis. Okay, so the geek is confused one more time because we need to assign all of these values on the pole 0 map. Let's do that. Okay, we have this map of the pole zeros. Start by at the angle of departures. Okay, angle of departures, of arrivals, and the values of the asymptotes. The asymptotes here is at 4, so it's out of range. So somewhere here we do have an asymptote of with an angle 180. So this goes to infinity here. Let's put the information of the arrival and departure angles. Okay, let's start doing the root locus plotting. We have the maps here, map of the 0 poles. Let's start adding or putting the information we got so far. We have the sigma or the position of the asymptotes at 4 somewhere here, okay, with the asymptote angle of 180. We have the break-in point here, and we have the angles of departure from complex poles, and angle of arrivals to the complex zeros. So we start drawing the branches. As we know, we have 3 poles, so we have 3 branches. So the rule says the branches are coming out from the zero, from the poles, and arrives or ends at the poles. So doing this or accomplishing this rule, we may draw this branch here using the guide of the angles of departure and arrival. Same on the other side of the complex or the real axis here, and we have another branch that coming out from this pole that goes to the zero at infinity. Okay, so the gig is now high since we had all the information and we draw the root locus. For extra information, you may need to know the MATLAB code that has been used so far to assist us drawing and computing some information for this root locus for this g of s. So here is the piece of that MATLAB code. It starts with finding denominator of the given g of s, doing the transfer function, trying to find the transfer function or producing the transfer function, and then extracting the pole zeros and gains of the transfer function, which was used in the first step. You may try to plot the 0 poles. You can use this command here, or you can also use this root locus command to draw the final root locus. For the computation of breakaway and break-in points, I already give this piece of code in the slides after when we compute the break-in and break-out points in the second step.